All right, this is the beginning of chapter 2, and there are a lot of little things in here. I'm going to try and be as brief as I can, but there are a lot of just little things to kind of get us started thinking about calculus. The first question I wanted to think about was find the vertical and horizontal asymptotes. And I really want to, at this point, just focus on the verticals. Okay, I just want to focus on that for now. Now, most people, I hope, will remember that the vertical asymptotes occur kind of as a first a thought when the bottom is 0. Whatever makes the denominator 0. So the temptation, I think, is for a lot of people just to factor it. Say, okay, well, adds up to 6 and multiplies to 8, x plus 2, and x plus 4, and you think, well, I'm done. You know, there it is. That's the asymptotes are going to be -2 and 4. But when you look at the graph, you see there's an asymptote at -4. We can definitely see the spiking here and here, but at -2 it looks just fine. And I hope then you remember, wait a second, if I also factored the top, x plus 2, x minus 2, those cancel out because x plus 2 divided by x plus 2 is just 1, and I'm left with this thing. And if you recall, when this cancellation occurs, this leads to what's called a hole in the graph. Okay? So we only have a vertical asymptote at x equals -4. Now, the horizontal asymptotes we're going to come back to, so I'm not going to worry about that a whole lot right now. In this case, if you think about a horizontal asymptote as just where it levels out, it's going to level at y equals 1. And there's a way to get that really easily. It has to do with the laws of dominance that you learned in pre-calc. In this case, we have the same power on top and bottom, an x squared and an x squared, so we simply use their coefficients to make a fraction. 1 divided by 1 gives us y equals 1. And there are other rules, but I'm going to address that later. Okay? So think about what happened here. This is going to be important. The difference between the asymptote, okay, where we actually have this spike, okay, happening here where we are undefined, and -2 where we have what's called a hole, where it's just a nice smooth graph, but in fact there will be an undefined spot right there. Now this is leading us to limits, and I apologize for the way this looks. I mean, let me just rewrite the equation right below it. Y equals 16t squared. 16. Okay, I've just got a little bit cut off here. Okay. The rock is dropped from a very tall cliff. The distance the rock falls can be found using that equation, where y is the distance dropped in feet in t seconds. Find the average speed. Well, I think a lot of people in science class think, well, speed is distance divided by time. In our case, we've got 2 seconds, and if you plugged 2 into this equation, 16 multiplied by 2 squared, so 16 multiplied by 4 is 64. So y is the distance it dropped. It traveled 64 feet. So its average speed was 32 feet per second. And that label, if you remember that, comes simply from your equation. Distance is feet, time is in seconds, so it's feet per second. Okay? Now, I think most people think about it that way, and that's fine, but I also wanted you to think about it graphically. Okay, I'm going to plot the 2 points here. 0, 0, which time 0, it's traveled 0, and at time 2, it's traveled 64. And if I connected those with a line and found the slope would represent the average speed. Okay? It's simply the slope connecting those points. Well, this leads to the next question. What if instead of wanting to find the average speed, I wanted to find the instantaneous speed? And if you think about throwing a rock off a cliff, of course, it starts off traveling slow, and as it falls and falls and falls, it falls faster. So the idea that its average was 32 feet per second, I hope you realize that at 2 seconds, it will actually be traveling faster than that. And how we'd calculate that is by finding the slope at 2. Well, easiest way to do that is to pick a couple of points right around 2 and calculate the y values. You know, maybe go really close, like 1.9. Plug that in and get the y coordinate. And 2.1 and get the y coordinate. Of course, you could get even better estimates by doing 1.99 and 2.01 and then finding the slope between those two. Unfortunately, what really would lead to the best answer is, of course, being able to get points so close on either side that they actually zoom right into 2. Well, this is where the idea of a limit comes in, because we can't actually just evaluate the point here at 2 because they'd be the same point. And we can't do this minus this and this minus this. If they're the exact same point, we get 0 over 0. And as I said, that leads us to the discussion of limits. So what is a limit? Well, a limit is simply a y value that a function approaches. And that is really the key word here, the word approach. Okay? And this is the book definition. If we can make the values of f of x close to L, as close as we'd like, by taking x to be closer and closer to c, but not equal to c. So the limit as x approaches c of a function is L. The translation is, it's the point that we approach from both sides of c. So let's go back to the opening problem, and I'm going to rewrite this with limits. Okay, but this is the same graph. Let's start with -2. Actually, let's start with -4. Let's do that one first. You'll notice here that we're going along -4 and we're spiking towards infinity. And then over here, we're going along towards -4 and we spike down towards negative infinity. Well, to have a limit, we must be approaching one y value from both sides of the function. So this one's easy because there is no limit. It does not exist. Whereas for -2, we're going along the function towards x equals -2, and we're approaching the y value -2. And from the other side, we're going along towards an x value of -2, and we're approaching the y value -2. And that means that is the limit at -2. It's simply the y value being approached by the function. And recall that we actually can't touch -2 because that's dividing by 0. There's a hole in the graph, but that doesn't matter. It's the y value it's approaching. Approach is the key word here in limits. It doesn't have to touch, it just has to approach. Now, I hope you think, how would I get -2 as an answer for this one right here without actually having to graph it? Well, let me factor it again. X plus 2, x minus 2, x plus 2, x plus 4, and remember, these cancel because they divide to be 1. Well, now, plug -2 in again. -2 minus 2 is -4. -2 plus 4 is 2. There's our answer. So if you plug a number in at first, and you're going to get something undefined, which is what would happen here. If we plugged it in, -2 squared minus 4 is 0, -2 squared is 4, minus 12 plus 8 is 0. We're going to get something undefined, 0 over 0. Try and factor it. See what happens, and then try it again. But you can also look at the graph, Of course, approaching negative 4, there's no limit. Approaching negative 2, there is. Let's look at one other example. I have 3x squared minus 6x over x. I'm starting with the limit as x approaches 1. And graphically, as we approach 1 from either side, it looks like we're approaching a y value of negative 3. And the nice thing is here, if you just plugged in 1, let's think about that real quick. If we just plugged in 1 here, 1, 3 times 1 squared is 3, minus 6 is negative 3, divided by 1 is negative 3. So our limit works out perfectly. We didn't have to do anything fancy. Next, we're going to approach negative 1. Okay, so let's look at the graph again. We're looking for negative 1 as we approach an x value. To me it looks about like negative 9 right there. Let's go to the other side. Coming down, it's approaching negative 9 again. I would guess that's the limit. But let me put negative 9. Let's just plug it in and verify that. 3 times negative 1 squared is 3, minus negative 6 is positive 9, divided by 1 is negative 9. So the picture and the algebraic reasoning work out the same. Well, in this next one, if I plug in 0, 3 times 0 squared minus 6 times 0, I get 0 divided by 0. Well, that doesn't work. We get something undefined. We get a hole in the graph. Well, let me just do a little bit of algebraic manipulation. Let me pull an x out. X on the bottom. And again, these cancel because x divided by x is 1. Now, let's try and plug in 0 again. So we get 3 times 0 minus 6 is negative 6. I'm going to write that down. But then let's look at the graph and verify it. As we're moving along towards 0, look what we're approaching from both sides. So even though there is a hole in the graph here because we got these things to cancel, we still have a limit that exists. Remember, it's the y value you're approaching.